Hi, this is Mr. Barron. I'm going to show you how to do problem number 59 from chapter 20 on electrochemistry. You can also reference this as instruction on how to find and calculate cell EMF, particularly under non-standard conditions. So in problem number 59, what we're dealing with is part A asking us to find EMF, but under standard conditions. Standard conditions, of course, are the concentrations are all the same, and the temperature is at 25 degrees Celsius. So the notation we use for finding EMF under standard conditions would be E naught cell. If we're finding E naught cell, we can use this table to get our answer. I like to follow the formula E naught cell equals whatever your volts are for the oxidation step of your reaction plus whatever the volts are for the reduction step. The reaction that's happening is you have solid zinc reacting with aqueous nickel, producing aqueous zinc and solid nickel. Actually, these are the two half reactions combined together. So my oxidation step is for zinc, my reduction step is for nickel. I'll start with the reduction step first for calculating the voltage. So that would be when nickel gains 2 electrons and becomes nickel. I can look that up on my table. I look it up and I look for nickel gaining 2 electrons, Ni2+, and I see it right here. It is negative 0.25. So that's how many volts. Well, that's the potential difference for this reduction step. Now for the oxidation step. Now when you look up this, which is zinc Zn2+, releasing 2 electrons, you're not going to find this on your table. It doesn't exist on here. The reason it doesn't exist on here is this is the standard reduction potentials. Reduction. So if you want to figure it out for oxidation, you have to take whatever the volts are for the reduction step of this reaction and then flip it. So I'm looking on here and I see zinc being reduced, Zn2+ being reduced, and it's negative 0.76. But because this is the opposite step, which is oxidation, I have to change the sign, so it's actually positive 0.76 volts. That's what I'm going to be working with. Now I can plug it in to find the standard cell conditions, E naught cell. And I'm just going to add my oxidation, which is 0.76, plus my negative 0.25 volts, and my cell under standard conditions will give me a voltage of about 0.51 volts. And that's the correct answer for A. The answer in the back of the book is slightly different, and it's because their table that they use is different than the one from the AP test. Alright, now we're going to get to 59B. The same question, but now we're not under standard conditions. Because we're not under standard conditions, we're given additional information about what's changed. And it's the concentrations. We now know that nickel has a concentration of 3.00 molarity before this reaction runs, and that zinc has a EMF, concentration, of 0.1 molarity. Okay, so now I need to use the Nernst equation. Right here is the Nernst equation. There's two forms of it. There's this form going from here to here. You use this one if your temperature is not at 25 degrees Celsius. You can plug in 25. Use this one if it is at 25 degrees Celsius. So when we're doing B, the only thing different is the concentration change, and that would be Q. So we have, not everything is at the same concentration, so we have to use Q. But I don't want to use the one on the left because I have to do more math if I use that. If I use the one on the right, since it's at 25 degrees Celsius, I don't have to plug in RT or Faraday's constant. So I'm going to write out the Nernst equation for this reaction at 25 degrees Celsius. So we do need our answer from A to be able to figure out this question, because you still have to plug it in under standard conditions, because it's going to be the difference between the standard conditions from the second part of this equation. So it's negative 0.0592 over n log of Q. Now n is the number of electrons, moles of electrons, not total number, but moles of electrons in this reaction that are being transferred. This one's pretty easy to see. You can see that 2 electrons are being transferred from the zinc to the nickel, and that's in our combined redox reaction. So the moles of electrons that are being transferred are 2 moles of electrons, so I know that my N equals 2. Q, however, is a little bit different. Q, I have to take the concentrations of the products divided by the concentrations of the reactants. Since nickel is solid and zinc is solid, they're not going to be in Q, which is my equilibrium expression. It's going to be Zn2 plus over Ni2 plus. So Q is Zn2 plus over Ni2 plus, and then I'm just going to have to plug in for zinc, it's 0.1 molarity, divided by nickel, which is 3.00 molarity. When I divide those two, I definitely get my Q. So when I plug in this Q and this N both into this equation right here, this is what it's going to look like. E cell is going to equal my voltage under standard conditions, my EMF standard, which is 0.51 volts. I figured that out from part A, minus 0.0592 divided by 2, because that's my moles of electrons, times the log of 0.1 divided by 3. When you do all of that, your voltage for the cell under non-standard conditions ends up being 0.554 volts. A little bit different from the back of the book, again, because of the usage of the different table if you were using the AP printout of the standard reduction potentials. Now I'm going to do another problem. The next problem I'm going to do is problem number 65. And 65 was one of the more challenging problems from this chapter, actually. So on problem number 65, what they tell you is to look at the diagram, or no, the figure in 20.11. So this is 20.65, that's the problem I'm going to be solving. Number 65, chapter 20, electrochem. And the cells that you're working with, I'm just going to draw the picture that they tell you to look at. And I'm not going to draw it that detailed. You've got the salt bridge going across, you've got 2 electrodes connected together. This electrode's zinc, and this one is hydrogen, H2. And they show what's happening is the zinc is dissolving into solution. So since this is oxidation, it's going from Zn to Zn2 plus, that's my oxidation. Always memorize red cat and ox. So anode is oxidation. Since oxidation is happening here, this is my anode. H plus is being reduced and going to H2, so red cat, reduction, cathode, so this is my cathode. What I'm going to do is I'm going to write out the half reactions for each of them. So the half reaction of my anode is Zn going to Zn2 plus and 2 electrons. This half reaction is H plus 2H plus 2 electrons going to H2 gas. Now let's think about this. By the way, this is solid too. The reason I wrote out the 2's here is because I need 2 hydrogens to make H2. And to balance out the charge, of course, 2 electrons have to be added here. Now I'm going to combine these half reactions, and when I combine the half reactions, what I end up having is Zn solid plus, so I'm taking all the reactants, adding them together, plus 2H plus. My electrons will cancel out because I have 2 electrons on the product side and 2 electrons on the reactant side. I don't have to worry about that. And then that produces Zn2 plus and H2 gas. Okay. So in problem number 65, what we have to do is calculate the pH. So this is an acidic solution because I have hydrogen ions that are being reduced and producing hydrogen gas. They do give you a lot of useful information in this. They tell you in this problem that the cell potential under the non-standard conditions is going to be 0.684 volts. Okay. Now what we can do is we can use the Nernst equation, because I'm going to rewrite the Nernst equation one more time. It's the one that I did in that last problem, and that is the cell potential is equal to the standard cell potential minus 0.0592 divided by the moles, and then that's the log of Q. All right, The cool thing is that we can think of what Q is. Q is going to be my products divided by my reactants. So that's going to be the concentration of zinc times the pressure, the partial pressure of hydrogen gas, divided by the concentration of hydrogen ions. But I have to square it because it's the coefficients too. So this is to the power of 2. And I'm not writing solid zinc in my equilibrium expression because it's solid. Remember, solids and liquids we don't write in equilibrium expressions. So what's cool is this can go in here. I know E cell. I can look this up with the table. I know the number of moles of electrons being transferred. And then I can solve for this H+, and that'll tell me the hydrogen ion concentration. So there's a lot of steps for this particular problem. So what I'm going to do is I'm going to start setting up the Nernst equation. So I'm going to put a box around this. This is what's on your formula sheet. I'm going to start plugging in numbers here. This is going to go there at 0.684 volts. If I want to look up the standard conditions, E cell not, for this, what I have to do is add the oxidation at half step and the reduction half step. I can use the standard reduction potential table, and when I do that, I'm going to skip that step, but because it's just like the last problem when I showed how to calculate this, you end up with 0.76 volts. And that's going to be minus 0.0592 over N, which is the moles of electrons being transferred. And let's go look at the top and see how many moles. Looks like 2 electrons are being lost here and 2 electrons being gained. So the moles of electrons being transferred, 2 moles. Then it's going to be the log, and they actually give you the concentration of zinc and they give you the partial pressure of oxygen. So it's the log of 0.3 times the partial pressure of the hydrogen, which they tell you I think is 0.9 atm. And wow, I'm running out of space, over H+ squared. I'm going to simplify this. This is kind of a mess because they tell you this number in the problem, they tell you this number in the problem, and you're solving for this. So let me rewrite this, and I'm going to simplify this down so that I'm left with just the variable and the quantity over here. So when I simplify all of this nonsense, what I end up with is 2.57 equals log of the concentration of that zinc, like I showed for Q, times the partial pressure of the hydrogen, which is 0.9 atmospheres, and then I have to figure it out for the hydrogen ions squared. So the rest of the problem is me solving for H+. So I take the anti-log of this, and then I do a bunch of algebra, and then I end up with my hydrogen ion concentration being 0.027. They're asking for the pH. Don't forget, you have to memorize this. pH is always, remember the P means negative log pH of hydrogen ion concentration. Sweet, now I just have to plug this in, and I find my pH is 1.56, which you can round to the correct answer you see in the back of the book, a pH of 1.6. If you have any other additional questions, please let me know.